Hey everyone, in today's talk I'm going to talk about how you should get started in CFD if you're a complete beginner, or maybe if you have a bit of experience in CFD but you want to enhance your skills and get much better at CFD. And to motivate today's talk, I have a few pictures of some recent simulations I've done. So on the very left hand side I have a large eddy simulation of a turbulent pipe flow where you can clearly see the unsteady nature of the turbulent eddies and the detailed structure of the eddies. In the middle here we have a natural convection simulation where we have a heated plate that induces natural convection of fluid flow in the ambient air. And on the very right hand side then I have a combustor that is driven by unsteady oscillations in the velocity flow. And you can clearly see the flame response in the combustor to the velocity fluctuations. And this is often used in combustion dynamics simulation to predict combustion instabilities in aircraft engines, gas turbine combustors, etc. So this gives a bit of a motivation on today's talk on what's actually kind of possible with CFD. So what we're going to talk about today is what is CFD, the process of reducing a real life problem that you see in everyday life and reducing that into a CFD problem. We'll talk about how the finite volume method works and how we obtain results using the finite volume method. We'll talk about some applications of the technology, even though they are so wide it's very hard to name them all. We'll talk about some of the errors that are involved in the process of reducing a real life problem into a CFD problem. Then we'll talk about what do you need to know in order to enhance your CFD career, and where do you start in your CFD journey, whether you're a beginner or whether you're someone who's run maybe a couple of simulations and you don't know where to go next, or you might have run multiple simulations and you need further knowledge in a particular area. So we'll talk about what I would recommend as a process for further enhancing your knowledge in CFD. So as an introduction then for complete beginners, CFD, or Computational Fluid Dynamics, is the process of solving a fluid dynamics problem by dividing it into discrete volumes, in other words, cells. So imagine every fluid flow is essentially governed by a field, a velocity field, a pressure field, where we have a solution at every continuous point. And what we're going to do is, instead of trying to solve the velocity, pressure, or possibly some other quantities at every single point, what we're going to do is we're going to divide the domain into chunks and solve it at discrete points. So this simplifies the problem over, rather than solving for the whole field or the whole fluid solution, we'll divide the domain into little chunks and solve the quantities of interest at these little chunks. And the center of these cells are called nodes, and this is typically where we get our, for finite volume techniques in general, and this is where we get our solution, at the cell centers. So what CFD does is it will take our domain, divide it into little chunks, and use the finite volume method, which is a numerical method, to solve for the quantities of interest at the cell centers, and it uses the finite volume method in order to do so. You may have heard of the finite element method before, and this is often used in structural mechanics to solve FEA problems, or finite element analysis problems. And the difference between FEA and CFD is that FEA typically solves the equations at nodes at the edges of the cells or at the corners of the cells. And the reason why we use the finite volume method in CFD over the finite element method is that in the finite volume method, all quantities are inherently conserved directly. What do I mean by that? I mean that we'll integrate the equations over each individual cell and ensure that mass, momentum, and other quantities that we want conserved are conserved. And this is important for fluid flow problems. So this is typically why the CFD applications use the finite volume method over the finite element method. It's that quantities of interest are conserved in the cells, which is a big advantage for fluid flows. And just an image of some cells that we can have. So in 2D we might have quad cells or triangle cells, and these are just different cell shapes. And in 3D then we have a multitude of different cells that could be used. We could have hexahedrons, tetrahedrons are quite popular. We also could have pyramids and wedges, or arbitrary polyhedrons. And these are used quite often now in ANSYS fluid meshing, where you can have arbitrary polyhedrons and it makes meshing quite efficient. So that's just an indication of some of the cell types that you can use to divide up your domain. Okay, so what is the process of taking a real life problem and reducing it into a CFD problem? And I really like going through this process in my head because it really helps me ensure that I'm understanding what the CFD problem is actually solving. And I would encourage you to go through this process yourself. Take a look at everyday examples you see in real life and ask yourself, how could you reduce that into a CFD problem? So here is an airplane wing. And if we want to reduce this real life problem into a CFD problem, there's a couple of steps we have to take. So of course, in this airplane wing, it's very, very complex. We have unsteady flow, we have trailing edge vortices at the edge of the wing. If we take a look at the geometry, it's very complex with lots of nuts and bolts. So we're going to make a lot of simplifications and assumptions in order to reduce the problem into something that's a little bit easier to solve. So we'll make modeling assumptions, geometry simplifications, and some simplifications on the boundary. So possibly some boundaries around the fluid flow, such as constant velocity and pressure, in order to simplify the problem into a model problem. A model problem is something that you can conceptualize in your head or draw on a piece of paper with a pen. And a model problem is typically a real life example, just reduced down to something a little bit more simple. And typically model problems is what you would solve in university, etc., where you would assume maybe steady flow, reduce the geometry to something more simple, reduce the forces into something that's into particular components that's easy to solve. So typically model problems is something that you can imagine in your head, a concept, or draw on a piece of paper, and this is your model problem, and this is a simplification of reality, right? And once you have your model problem, the equations of fluid flow still hold here. So the Navier-Stokes equations for momentum and the continuity equation, etc., these will be field equations all around our fluid domain that govern the quantities such as velocity and pressure, right? Now we take our model problem and we then reduce it to a finite volume model. And in doing that, what we do is we take the partial differential equations that govern the fluid flow in our model problem and we reduce it into algebraic equations. And the reason why this is a big advantage for CFD is that it makes it far easier to solve. And what is happening when we're reducing the partial differential equations into algebraic equations is what I mentioned on the last slide. We're taking the field equation and we're saying, look, we don't want to solve it at every single point. We just want to solve it at multiple discrete points, and that's good enough for us. So that's what's happening when we're reducing our model problem into a finite volume model. And we do so by creating a mesh, where creating the mesh is called the discretization process. And that's the process of splitting our domain into little chunks here. And this is just an example of an airfoil that I have. And you can see the domain is divided into little chunks, and this is the discretization or the meshing process, and this gives us our finite volume model. Now, once we have our finite volume model, then we can use numerical techniques such as computer algorithms and matrix methods to solve the equations to get the quantities of interest at the cell centers, and then we can create our contour plots and verify and validate the results. So you can see there's a lot of simplifications and assumptions that are involved in going from a real life problem all the way down to a CFD problem, where in this case here we have a 2D airfoil that's representing a real life airfoil here. So there are lots of assumptions and simplifications that are made in the process of going from a real life problem down to a CFD problem. So let's talk about the modeling process. So the modeling process is where we take our real life problem and we make some simplifications and we neglect things that might not be as significant in the flow or environment, and we reduce it down into our model problem that we might conceptualize in our head or draw on a piece of paper. And model assumptions might be, for example, assuming steady flow. So if an airplane is flying at constant speed, it would be a pretty good assumption to assume steady flow, that at time 10 seconds and at time 100 seconds, the flow is going to be pretty much the same on this airfoil, so we would assume steady flow. Other examples would include incompressible flow if there's no large density changes, if adiabatic flow if there's no large temperature gradients and no heat transfer, inviscid, etc. So this is essentially the process of taking non-negligible effects and reducing that then into our model problem. So steady flow, adiabatic, etc. We also have some geometry simplifications that's going to make the problem far more easy to solve. So for example, if we look at the airplane wing with all the complex structure here, the flaps, the nuts and bolts, other parts attached to the wing, the aircraft engine, if we were modeling this in CAD, we might just model this wing as a flat piece along here, nice and smooth, just to simplify the problem and make it far easier to solve. So we might remove some sharp edges, flaps, uneven geometry, and we'll neglect manufacturing tolerances. If the geometry is symmetric, we might make an axisymmetric geometry, etc. So we will reduce the geometry from something complex into something a little bit more simple in our model. And lastly, then we'll make some boundary simplifications. So typically in CFD, you use a constant velocity inlet, which would have a constant velocity at some point upstream of your part, and a constant pressure outlet. And these velocity inlets and pressure outlets will assume constant pressures and constant velocities and constant levels of turbulence. So this is some simplifications about the surrounding flow and the boundary conditions around the flow that'll make solving the problem just that little bit easier. So how do you decide what assumptions you can make if you're taking a real life problem and reducing it into a conceptual model? What assumptions can you make? And how you decide on what assumptions and simplifications you can make, I would highly recommend asking yourself, what is the output of your simulation? And that will help you in determining what assumptions you can make. So taking this airplane wing as an example, if I wanted to figure out what the frequency of the vortices shed from the edge of this wing were, I would have to model this in 3D, and I would have to model unsteady flow. So knowing that my output of the simulation is the frequency of the trailing edge vortices, and that's my output of the simulation, instantly I know, okay, well, it has to be 3D because trailing edge vortices are a 3D effect. And if I want to find the frequency of the vortices, well, that means it has to be an unsteady flow, because if it were steady, there would be no frequency. So if you're taking a real life problem and you want to find out what simplifications and assumptions you can make, I think a great exercise to do is to ask yourself, what is the output that you need? Is it the lift coefficient? Is it the temperature? Is it the velocity? And once you know what the output is that you're looking for, then you can determine what assumptions and simplifications you can make. And I think this is a great exercise to do in CFD anyway. Long before you touch a computer, you should know for yourself, okay, what do I need to know? Do I need to know the temperature? Do I need to know the velocity? Do I need to know the pressure? What can I neglect, and what assumptions can I make? That will make solving CFD far easier, because you'll know exactly what level of detail you need to put into your problem. And all of these assumptions and simplifications leads to modeling errors. So this is one of the errors that we introduce in order, once we start modeling a real life problem and creating a conceptual problem. Okay, so once we have our conceptual problem, which we might have thought about in our head and drew on a piece of paper, then we have to reduce it into a finite volume problem. So how do we do this? Well, of course, we discretize the domain into small little chunks. We take our fluid continuum and we apply the governing equations to each of these little chunks, okay? And yeah, this is the process of CFD. Instead of solving the solution field everywhere, we're going to solve it just at these discrete control volumes. And as I said before, the process of taking the smaller problem and dividing it into little chunks is called meshing or discretization, where we reduce the partial differential equations into the algebraic equations. So how do we get results out of our finite volume solution? The goal here, remember, is to take our partial differential equations and to create a set of algebraic equations. So how we do that is we take the partial differential equations that govern this fluid flow, the Navier-Stokes equations, the continuity equations, and we convert it into integral format. The next step then is to integrate these governing equations over each cell volume in order to form a set of algebraic equations. And this is what I talked about in the first slide, where the finite volume method will conserve quantities, because what we're doing is we're going to integrate the governing equations over each cell. So we're going to ensure, for example, that momentum, energy, and mass, for example, would be conserved in that volume. So in integrating the equations over each cell volume, we now have the governing equations in integral form, which, as I should have mentioned, these integral equations will be exact. So they'll be the same exact solution as the partial differential equations. But once we have the integral equations, then we can reduce the integral equations into algebraic equations. And when we do this, when we take the integral equations and we reduce it into algebraic equations, this introduces what's called the discretization error. And this is the error that is involved in taking partial differential equations that govern a field and integral equations that also govern a field and reducing it into solutions at just singular points or singular cells. So this is the discretization error. And the reason that we're changing the governing equations into algebraic equations is that we can then use linear algebra and much more simple mathematics to solve these equations. But before we can solve these algebraic equations, so the algebraic equations for each cell here, so for example at node 1, node 2, before I can solve these algebraic equations, there are actually some more complexities that need to be dealt with. And one of the main complexities that need to be dealt with is that the governing equations for fluid flow are actually nonlinear. So we have our set of algebraic equations, and these are going to have u squared, v squared terms and cross terms such as u times v, which need to be dealt with before we can actually solve the set of algebraic equations using linear algebra. So how we solve for these nonlinear terms is we use the Newton-Raphson method, and you may have done this in university in a numerical methods course, but essentially the process of the Newton-Raphson method is to take an initial guess value and add on a certain change to that guess value, and you can take your new value and you can calculate what the residual is. So in other words, how close were you to the actual solution? So this is an iterative process. So any non-linear term that we want to solve for, we need to make a guess value, sub it into our equation for the Newton-Raphson method, and then we can check how close we were to the actual solution. And if we were too far off, we take our new value and we iterate again, and we iterate again, we iterate again until we're close enough to where we want to be. And this initial guess here that we provide for the nonlinear terms is actually what we do in CFD when we initialize the solution. So if you've ever run a CFD simulation before, you'll know that you'll have to initialize the solution. In ANSYS, for example, you can use standard or hybrid. And what this does is it essentially just assigns an initial velocity and pressure to each one of the cells so that the solution can go through this iterative process of solving for nonlinear terms in the cells. And just a little note on how the Newton-Raphson method works. We have our initial guess value here, and then plus the derivative of that guess. So the reason I have 2u guess here is that's the derivative of u squared, and then times a small change in u, and that delta u is shown on the graph here, and the 2u guess shows the slope, the derivative essentially of this curve. So that's how the Newton-Raphson method works, and I'll go ahead and show you how we would solve for nonlinear terms and what residuals are. So say for example we take a u guess when we initialize the solution and we solve for u new. What we do then is we take our new value for u squared and we sub that into our equations, so our governing equations for maybe mass, momentum and energy, and we check if the quantities are conserved. So in other words, is the equations for continuity satisfied? Is the mass that entered the cell the same as the mass that left the cell? So for example, if 5 kg came into the cell and 9 kg left, we know that mass isn't conserved, it's being created in the cell, and that's wrong, so we would be off and we need to calculate a new value for u squared. So we sub our u new value into the cells and we determine if the solution is correct or not, or how far off it is. And how far off we are is called our residual, and you will have seen this in CFD when you see your residuals converging or possibly diverging when you're solving a solution. So we take our u new value, we sub it in here. Let's say for example our equation was ax squared plus bx plus c equals 0, and that's our solution, and with a tolerance of 0.01. So in your CFD simulation, you'll set the residual tolerance to, it's typically at 0.001 as standard, but you might change it to 1e to the minus 6 if you choose to have a little bit of a more accurate solution. So if 0.01 is our tolerance and we sub our u new squared value into our governing equations and we get 0.01 here, then we have to iterate again because it's not within the tolerance that we've set. So we iterate again, we get 0.09 for example, then say we get 0.02 until finally we stop iterating once the residual value drops below our tolerance. So that's how the nonlinear terms are solved for in the finite volume method. So once we've taken our partial differential equations, changing them into integral form, which is equal to the differential form, then taking that integral form and changing it into a set of algebraic equations. Once we deal with the nonlinear terms, then we have everything we need to find the values at the cell centers. So that would be values of u, v, w, and p, and possibly some more quantities if you're solving a more complex solution. And once we have these cell center values, then we can get our contour plots. And how we get these contour plots is simply by post-processing the results of these u, v, w, and p values. And I think this is another important thing to note. In CFD, we're not solving a set of equations that gives us our color plots. This is simply a post-processing of the u, v, w, and p results at the cell centers. So this averaging over here, for example, is just simply averaging over cell centers. So the contour plots are not a direct output of the equations. Only the cell centers are. Everything else that you see or calculate, maybe the lift coefficient, drag coefficient, is a function of what values you calculated at the cell centers. So if you haven't calculated your cell center values accurately, everything else will be off. So then once we get our contour plots and our results from our CFD, we have to verify and validate the results. So verification of the results is comparing our CFD solution that we see on screen to the model problem that we conceptualize in our head and can maybe draw on a piece of paper, for example. And this might be, for example, comparing velocity at a certain point in the flow that we know from our model problems, such as maybe having a look at the velocity at the inlet, having a look and see if the no slip condition is verified at solid walls, for example, etc. So verification is comparing our model problem, our conceptual model problem, to our CFD problem result on the screen. And validation is a little bit different. Validation is when we compare our CFD results to reality. So we might conduct an experiment, for example, and validate that the CFD that we're seeing on screen is representative of reality. So validation, we're comparing the CFD results that we see on screen to actual reality, and verification is understanding if our CFD problem that we see on screen is representing the model problem that we conceptualized and created that finite volume model from. The important thing here is that CFD, the main value in CFD is in qualitative results over quantitative results. So typically in CFD, we're not looking to get the exact lift coefficient or the exact temperature at a particular location, but we're looking to see, does the CFD model follow the trends of what we would expect? So if we increase the angle of attack of the airfoil, does the lift coefficient go up as we would expect? Maybe if we change the flow velocity, does that change the temperature in the right direction? Does temperature go up and down? If we change the geometry, does that cause lift coefficients go up and down, velocities to go up and down, etc.? So it's about the trends, and does the CFD problem accurately represent what reality is following in terms of trends, not exact numbers. And this gives us valuable insights. So say, for example, you conducted an experiment and you knew the velocity at certain points in the flow, and then you model that using CFD, and then you can verify that the velocity at certain points in the flow is close enough to your experiment. Then you can take a deeper insight into that flow and maybe visualize some effects that you wouldn't be able to see from reality. So that's the real value in CFD, is that we can take a look at the qualitative results and maybe take a deeper understanding of the flow field that we would not have been able to see from reality. Another valuable thing we can do is we can change the operating conditions of CFD far easier than experiments. So say, for example, you calculate the lift coefficient of a particular airfoil in an experiment, and that matches with your CFD. Changing the geometry of your CFD simulation and evaluating how that affects the lift coefficient is very simple to do. You go in, you change your geometry slightly, and you rerun the simulation. But in an experiment, for example, you're going to have to manufacture that whole airfoil again and rerun the whole experiment all again. So if we can get one simulation that matches experiments, we can then make small tweaks to the CFD and see how changing different parameters affects the output of our solution. So this is another really valuable thing about CFD, is that we don't have to repeat experiments over and over again for every single operating case. We can use CFD to do that. So some applications of this technology. The applications of CFD are growing every day, and there are so many applications to date. So the most popular by far is aerodynamics and hydrodynamics. So anything that involves fluid flow using air and water, such as aerospace, aeronautics, sailing, for example, etc. We also have turbo machinery, compressors, pumps, gas turbine engines in industrial applications or in aircraft engines. Combustion applications, there's huge value for CFD in order for reducing emissions, reducing combustion instability in different engines. We can do force analysis, so taking a wind turbine or a pump and evaluating the fluid flow over it, and then calculating the stress in that wind turbine or pump, for example. And heat transfer, a lot of applications for heat transfer here. So as electronics parts are getting smaller and smaller, the heat flux is going higher and higher because the cross-sectional area of these components, such as the CPU, for example, is getting ridiculously small. So the amount of heat flux over these components is very high. So the cooling of these applications uses CFD quite a lot in order to improve the design. Another few examples: heating, ventilation, cooling, biomedical, marine, and really there are so many more that aren't mentioned here. So let's talk about the errors that are actually involved in going from this real life problem into a CFD problem. The first set of errors is modeling errors. So remember, when we're taking a real life problem and creating a model problem, such as a CAD model and a conceptual model, etc., we're not going to be able to accurately capture the geometry in full, or if we do, we most likely are going to make some simplifications to make solving this problem a little bit easier. So we have modeling errors induced with this. We also have modeling errors with the assumptions we made about the flow or environment, such as steady, adiabatic, and maybe some boundary simplifications as well. So this is all modeling errors in taking a real life problem and creating a conceptual model. Then in going from a conceptual model and creating a finite volume model, we introduce more errors. So we have our discretization error, which is taking the field equations that govern this whole fluid flow and reducing it into just the solution at particular chunks, and that's our discretization error. We also have our linearization errors. So we have nonlinear partial differential equations that we're going to then use the Newton-Raphson method to linearize these equations so we can solve them easier, and this introduces a linearization error, which is reflected in the residuals in CFD. And then when we have our set of algebraic equations here to solve, of course we're going to have some more errors from the computer, such as computational errors due to the fact that we're using floating points in the computer, some numerical errors, and also user input errors. So I've done this many times myself, to run a simulation and just simply use the wrong velocity, or to forget to turn on heat transfer, etc. So we have lots of user input errors as well in taking the user that's using a CFD finite volume model and trusting that they've done everything to conceptually model this in the correct format. So there are user input errors involved too. So if you're a complete beginner and you just want to know, okay, I want to get started with CFD, what do I need to know? So the first thing you definitely need to know before you get started is the basics. So any university introductory course to fluid dynamics or fluid mechanics too, to learn about Newton's law of viscosity, to solve some simple problems such as flow over a flat plate, flow in a pipe, for example, with some friction factors, Bernoulli's equation, these basic concepts of fluid flow and generally how fluids behave. You absolutely need the basics, of course, before we can move to these complex problems with CFD. Then we need to know about problem definitions. So we need to know about the different methods of in what level of detail do I need to model my problem. And in order to understand this, we need to know about the conservation equations, and we need to know about turbulence and turbulence modeling. So this will tell us in what level of detail we need to solve our problem. So on the right hand side here, I have an image of a DNS of a flame, so a direct numerical simulation. And this is a turbulent flame where the solution here solves for every single length scale of eddies. So all the small eddies, all the large eddies, and you can see the level of detail in this simulation. And for example, if we did a RAN simulation of this flame, we would get a mean flow over this whole flame where everything would be averaged out and a much more smooth contour, such as the images I showed in the first slide. So we need to know what level of detail are we going to solve here and what's important to us. And in order to understand that, we need to understand the RAN's equations and a little bit about large eddy simulation and direct numerical simulation, how turbulence is modeled, and how do we solve for turbulence with our equations. Once we know about our problem definition and what level of detail we need to go into with our problem, we then need to understand a little bit about what's going on under the hood. So we talked a little bit about it today, the finite volume method. How do we mesh? What different discretization schemes are used in CFD, such as upwind differencing, central differencing, etc., and different solution algorithms that are used under the hood, and which is most suitable to our particular application, such as are we using a compressible flow, an incompressible flow. This will change what a solution algorithm is probably best for us. So the simple and piezo algorithms are two very popular algorithms in order to solve a CFD problem. We also need to know about where all the buttons are and what do they mean. So this can be done by reading the manual or just by following different tutorials. But of course, we need to know, once we have our conceptual model problem and we want to model that in CFD, we need to know actually how to do that. How do I properly initialize my solution? How do I get the boundary conditions that I want? How do I get the results and the output that I actually want? So we need to understand, whatever software we're using, how to actually model the problem in the way that we want to. And then of course we need to know about post-processing the results, having a look at if we're wrong, if we're correct, how do we actually determine this, etc. So these are what I would call the 5 big pillars of CFD to get yourself started, of what we need to know and what areas we need. And of course, if you're doing any specialized applications such as combustion, heat transfer, turbo machinery, supersonic flow, you'll need to know the fundamentals of this specialized area and probably how different equations are modeled in this area. So for example, if you were doing combustion, you would need to know the fundamentals of combustion, and you would also need to know the combustion modeling equations and how combustion is modeled in CFD as well. So that adds some extra complexities into CFD as well if you're doing any specialized applications. Okay, so now that we've covered what you need to know, let's talk about where you should start. So most people start here at the very basics. They've done a fluid mechanics course in university, or done a couple of model problems, for example, and most people start here, and that's good. So we take our this is a book I highly recommend for anyone doing the basics, Fundamentals of Fluid Mechanics. This will just teach you how to solve some simple fluid problems with a piece of pen and paper, or with a calculator, and that's the basics to understand fluid flow and how fluids work. And then most people in the university course start with the basics and then go to something more complex straight away. So you go straight to a CFD solution. You might get an assignment, for example, and then you'll move to where are all the buttons and what do they mean. That's all you want to know is how do I use ANSYS? How do I use star CCM plus? How do I use OpenFOAM? And you get your contour plots and you get your assignment done. And then when doing your assignment, when doing your first CFD simulation, you might just delve a little bit into problem definition. So you might understand what you solved for. Okay, well, I assume steady flow, and I ignored viscosity by using an inviscid flow, etc. So you'll delve a little bit into problem definition too. And you might do a small bit of error estimation too, where you take the results you got from your simulation and compare it to some experimental data or to some results from the literature, for example. And then most people stay here in this kind of cycle of where are all the buttons and what do they mean? How do I use ANSYS? How do I simulate this? How do I use star CCM? How do I conduct a certain simulation? And I highly recommend that you don't stay at this stage where after you've run a couple of CFD simulations or your first simulation, then just focusing on a particular software. What I recommend is going through these 4 branches here and dabbling into problem definition and really understanding what you're actually solving for and in what level of detail. And then taking a look at what's happening under the hood, the finite volume method, discretization, what's actually happening in the computer. A little bit into where are all the buttons and what do they mean. What you might have a look at a user manual and have a look at the different options you can use in a software, and having a little bit of look at error estimation and how to improve maybe your mesh quality or your results quality. So any good CFD engineer will delve into these 4 areas, as this is what makes a good CFD engineer that can use any code, and it really cements your understanding when you understand these 4 areas in detail and then advance into even further areas of CFD. And also I've noted here that learning one of these sort of areas will complement another area. So I have an example here. If you understand the assumptions that you make in a problem, it will help you verify and validate your results. So if you know that you've assumed a steady flow, then you'll know you can verify and validate your results against steady results where there's no vortex shedding, for example. Another example would be if you understand what's under the hood and how the finite volume method works, it's going to be far easier to understand the different buttons and answers and what they mean. You'll see the simple algorithm and you'll say, oh, okay, I understand what that means now, or the piezo algorithm, and you'll understand whether it's useful in this case, in your simulation case, to use that algorithm or not. So learning what's under the hood will help you understand what buttons to use and what they all mean. So here's some recommended reading for those who want to start. If you've never done the basics before, never done fluid mechanics before, then I'd recommend going to this book, The Fundamentals of Fluid Mechanics by Munson et al. Also then, if you want to jump from this stage of going from the basics to starting actual CFD, this is a great introductory book by Versteeg, an introduction to computational fluid dynamics, and this book will help you understand the problem definition, so what are we solving for and in what level of detail, and what's happening under the hood a little bit too. So it talks about different solution algorithms, the finite volume method, turbulence, how turbulence is modeled, etc. So this is a very good book from jumping from that basic stage into that starting a CFD stage and understand what's going on. Then if you want to go even further and we want to understand more than an introduction, this is a great book by Fertziger, Computational Methods for Fluid Dynamics, and this will help you understand even more then, especially after having a look at previous books before, in terms of the problem definition, so what are you actually solving for and in what level of detail, and what's happening under the hood, some more about the finite volume method, some more details about how solutions are actually solved, about meshes and how that affects how the solutions are solved, etc. And then for where are all the buttons and what do they mean, I would recommend going to the manuals for maybe ANSYS or Star CCM, and OpenFOAM have a great resources out there. And also with my channel, what I hope to do is to sort of give some tutorials here to show you how to use the software and get going with that practical example, because I do think it's important to go from the basics and then to run a practical example and then refer to the textbook and keep doing some practical examples. So what I hope to do with this channel is to provide you guys with practical examples so you can understand how to use the software, how to get results, and then that will motivate you to jump to the textbook and understand, okay, well, what's actually going on here. And while I do these tutorials, I also would like to mention that I will be jumping to different areas such as problem definition and what level we're solving, what's happening under the hood. So you'll notice in some of my tutorials I do explain, okay, we're using this algorithm for this reason, or I initialize this because this. So I do like to incorporate in my tutorials some explaining to what's actually going on too. And then to determine whether you're correct or whether you're wrong, a great way to do so is the scientific literature. So look up on Google Scholar, lift coefficient of airfoil CFD, or turbulent flame RAN simulation CFD, and have a look at some of the other results that are out there. Have a look at some experiments that were done, and there are some error estimation techniques too, that can be used for meshes, for example, and that will help you determine what kind of errors and how correct you are with your simulation. Okay, so in the next video then, what I actually will go through is the conservation equation. So how is the conservation of mass and the conservation of momentum derived for those that have maybe done their fundamental fluid mechanics. Maybe you've done a couple of CFD simulations before, but you're not sure exactly what's going on under the hood. You're not exactly sure what level of detail you're solving your problem in. So what I'll do is I'll go through deriving the equations for the conservation of mass and momentum, and then from that then we'll be able to derive the RANS equations, so you'll know in exactly what level of detail is being solved for your fluid flow and when you run a CFD simulation. So I hope you enjoyed. Again, if you have any suggestions for some videos you'd like to see, let me know in the comments, and I look forward to hearing your feedback.